Assalamualaikum and good day everyone. We are from Group 15 and today we will present our project on the population dynamics of mycoparasites and their invertebrate hosts. Throughout this presentation, we will explain the mathematical formulation, the steady state analysis, stability analysis and also the simulation results. These are our group members. So without further ado, let's begin with the introduction.
My name is Nora Farini. I will present about the introduction, mathematical model and formulation, and also the implication. This paper 2 describes the population dynamics of mycoparasites and their invertebrate hosts. The model divides the host population into susceptible and infected classes and incorporates free-living infective stages in the environment. It is known as an eco-epidemiological model because it combines ecological process with epidemiological process, where ecological components contents of host birth, death, and population growth, while epidemiological components contents of transmission, recovery, and disease-induced mortality. There are four variables, which is X is number of susceptible hosts, Y is number of infected hosts, W is number of infected stage, and H is total number of host population. While there are 8 parameters, which is A is host birth rate, where the new hosts are produced, B is natural death rate of hosts, where the mortality are related to the disease, V is transmission coefficient that measures how efficiently environmental infective stage infects susceptible hosts, Gamma is rate of host recovery from infection, R is intrinsic growth rate host population, where R equals to A minus B, Alpha is disease-induced mortality rate, that additional death rate experienced by infected hosts due to infection. Lambda is rate of production of infective stage, which means rate at which each infected host releases infective particles into the environment, and mu is mortality rate of free-living infected stage. That means natural decay or loss of infectivity of environmental pathogen particles. From equations 59 to 62 of paper 2, the model is formulated by using few assumptions. First, the host population consists of susceptible and infected individuals. Second, infection occurs through environmental transmission, where it depends on interactions between susceptible hosts and environmental infective stage rather than direct host contact. Next, recovered hosts return to the susceptible class, which means recovered infected hosts leave the infected compartment and re-enter the susceptible compartment. Next, infected hosts produce free-living infective stage. Each infected host contributes infective stage to the environment at rate lambda. The last one is infective stage decay naturally in the environment. Environmental infective stage lose viability or die at rate mu.
Hi, I am Siti Nurul Atika and I will present to you the steady state analysis of the model. To determine the steady state of the system, we first set all time derivatives equal to 0. This means that the population is no longer changed with time and the system is at equilibrium. Next, we solve the resulting algebraic equations step by step. From equation 61, we obtain H and denote it as equation 1. Then from equation 62, we obtain W and denote it as equation 2. From equation 60, we obtain X and denote it as equation 3. Finally, from equation 59, after rearranging and simplifying, we obtain another expression for X and denote it as equation 4. Since equations 3 and 4 both represent X, we equate them and also substitute the expression for W. After further simplification, we obtain an expression for Y. Once Y is known, the values of X, H and also W can be found by substituting back into equation 1, 2 and also equation 4. This process allows us to determine all equilibrium points of the model. From the steady state analysis, 2 equilibrium points are obtained. First one is disease-free equilibrium, where we consider Y equal to 0, then eventually X, H, W also becomes 0. This equilibrium corresponds to the absence of both infected hosts and also the free-living infective stages. In other words, it's like the parasite is unable to persist in the host population. Second one is endemic equilibrium, where we assume Y equal to Y star and eventually we get X star, H star and also W star. Here, these variables are non-zero equilibrium values. So basically, these represent the coexistence of susceptible hosts, infected hosts, and also the free-living infective stages. Therefore, the disease remains present in the population at a constant level over time. According to Anderson and May, the enemy equilibrium is biologically feasible only when certain conditions are satisfied, particularly when the disease-induced mortality rate exceeds the intrinsic growth rate of the host population, that is alpha greater than R. If these conditions are not satisfied, then the equilibrium may produce negative population values and basically has no biological meaning. Therefore, the disease-free equilibrium describes the disease extinction, while the endemic equilibrium describes the long-term persistence of the parasite within the host population.
Hello, my name is Zulaika. Now I'm going to present about Jacobian matrix and stability. To compute Jacobian matrix, first we need to do the first order partial derivative for the equation dx over dt, dy over dt, dh over dt, and dw over dt. And after we do the first order partial derivative, we will get this form of Jacobian matrix. After that, we will substitute all the parameter value in, and then we will get the general Jacobian matrix. After we get the general Jacobian matrix, we will calculate the stability analysis of the extinction equilibrium. We will start by substituting the x equal to 0, y equal to 0, w equal to 0, and h equal to 0 into our general Jacobian matrix, and then we will get this form of matrix. After that, to find the eigenvalue, since this matrix contains of several blocks of zeros, we can read the eigenvalue from its diagonal structure, or we can also calculate it by computing its determinant equal to 0. By expanding the column, it will use the four distinct eigenvalue directly, which we get our lambda 1 equal to 3, lambda 2 equal to negative 8, lambda 3 equal to 3, and lambda 4 equal to negative 14. By seeing this value, we can conclude that since the eigenvalues of Jacobian matrix consist of both positive and negative point, so it is an unstable saddle point. Next, we will calculate the stability analysis of the coexistent equilibrium. We will substitute the value of x equal to 70, y equal to 52.5, h equal to 122.5, and then lastly w equal to 60 into our general Jacobian matrix that we have computed before. And then we will get this form of Jacobian matrix. After that, we will find the eigenvalue by compute its determinant equal to 0. By expanding the column from the matrix that we compute before, we can see that it yields the four distinct eigenvalue as below, which is we get our lambda 1 equal to 3, lambda 2 equal to negative 35, lambda 3 equal to negative 1.125 minus 4.019 I, and lastly our lambda 4 equal to negative 1.125 plus 4.091 I. As a conclusion for this point, since the eigenvalue consists of both stable eigenvalue, which is the negative real part, and unstable eigenvalue, which is the positive real part, so we can conclude that the equilibrium point is unstable saddle point.
My name is Amira Patricia and I will present about the numerical finding. So from the paper, we get the estimate of the parameter, and from analysis of steady state before, we substitute the value of the parameter into the equation. Then we will get the steady state as shown in the slide. So as steady state at 1, as mentioned before, in steady state part, the steady state 0, 0, 0, 0, all the population will be collapsed. But at the steady state 2, the steady state 70, 52.5, 122.5, and 60, the population will coexist. Next, for the phase portrait part, I'm using MATLAB to show the numerical finding. So at the first steady state, we can see it is an unstable saddle. For the second steady state, it is also an unstable saddle. Thus, all the numerical finding will agree with the theoretical analysis. Is about a time series plot. So at first, we're looking at the initial state from T0 to T1. At T0, the infected host, that is Y, starts slightly higher than susceptible, that is X, which begin near 0. This is because of the healthy host pool is so low. Microparasite transmission is inefficient, causing the disease to spread slowly at first. Between T0 and T1, both curves grow slowly and remain tightly clustered. However, because the healthy hosts are reproducing without resource competition, they quickly build a momentum. Around T equal to 1, the healthy population crosses a critical threshold, which allowing the blue line of X to officially overtake the red line of Y. Okay, next we move into the divergence state from T1 to T4.5. The gap between our curve steadily widens as the blue line of X pulls ahead. This happens because the host reproduction temporarily outpaces parasite transmission. Since invertebrates reproduce rapidly and face little competition early on, the healthy host population explodes exponentially. While the affected population Y is also growing, its spread is bottlenecked by the physical time it takes for the microparasite to replicate inside the host and infect the new individuals. As a result, the healthy host successfully outrun the disease during this phase. And finally, from T4.5 to T5, we see a dramatic simultaneous surge as the system hits a high density transmission tipping point. Because of the susceptible host population X grows so massive during the divergent phase, the microparasite now has an overabundant supply of targets. This triggers a hyper-efficient wave of mass transmission, causing infected hosts to skyrocket. Furthermore, because invertebrate lack an adaptive immune system to slow down infection at a population level, the disease spreads unchecked, forcing both curves upward in a final, runaway exponential explosion. So to conclude all of this, while the infected host Y had the initial head start, the susceptible host X poses a significantly higher growth rate parameter. This advantage allows the healthy population to overtake the infected curve early on and maintain an absolute dominance throughout the rest of the time series.
For the numerical approach, we varied the eco-epidemiological parameter, which is the host intrinsic growth rate R, and observe how each equilibrium changes. The four panels shows the equilibrium values of susceptible host X star, infected host Y star, total host H star, and free living infective stages W star. We observe that when R is smaller than 1.4, the equilibrium values of X star, Y star, and H stars are negative, making the coexistent equilibrium biologically infeasible. Once R exceeds 1.4, these equilibrium values become positive, indicating that coexistence becomes biologically feasible. Therefore, from the numerical bifurcation analysis, the threshold value is approximately RC equal to 1.4. To make the threshold easier to observe, we focus on the infected host equilibrium Y star. The dashed red curve represents negative values of Y star, which are mathematically valid, but biologically impossible because population sizes cannot be negative. After crossing R equal to 1.4, the curve becomes positive and is shown as a solid red line. The dotted vertical line marks the threshold where this transition occurs. This graph clearly illustrates the switch from an infeasible equilibrium to a feasible coexistent equilibrium. Next, we verify the numerical threshold analytically. Solving the equilibrium equation gives the expression y star equal to 140r over 5r minus 7. The denominator becomes 0 when 5r minus 7 equal to 0, which gives the exact threshold, which is r equal to 7 over 5, which is also equal to 1.4. This agrees perfectly with the numerical bifurcation diagram, confirming the correctness of the numerical analysis.
Next is eco-epidemiological implications. First, analytical and numerical results are consistent with each other. Next, environmental effective stage, which is W, play an important role in disease persistence because it allows the disease to continue spreading within the host population. The host growth rate, which is R, significantly influences the long-term dynamics of the system. Changes in the host growth rate can affect the survival and coexistence of both host and pathogen populations. A threshold value RC equals to 1.4 determines the feasibility of host pathogen coexistence. The effective disease management should focus on both infected hosts and environmental pathogen recipients, because controlling infected hosts alone may not be sufficient because pathogens can still persist in the environment. The last one is the model can assist conservation biologists, wildlife managers, and policymakers in developing disease control strategies. That's all from us. Thank you.